So, good afternoon, ladies and gentlemen. Welcome to this afternoon's joint Heidelberg Astronomical Colloquium. And this week we're staying on the topic of star formation in galaxies, also on relatively small scales in galaxies. And, but we're moving more to the observational focus. And we have one of the absolute leaders in the field of multi-wavelength observations of galaxies to tell us all about it this week, Eva Schinnerer. Eva started her scientific career actually doing a diploma in geophysics, which she skillfully managed to manipulate such that the title of her thesis was Star Formation in the Nuclei of Infrared Luminous Galaxies. That's quite an achievement. And then, of course, after that, she moved on to do her PhD in Garching at the same place with Reinhard Genzel as her prime supervisor, where at that early stage in doing your thesis on Seyfert galaxies, nearby Seyfert galaxies, you already got into the observational mode of doing radio interferometry, looking at gas in the galaxies with the Plateau de Boer interferometer. And thereafter, the logical step was move across to the US, where you did a postdoc in the Owens Valley Observatory, working on the interferometer there, with working with Nick Scoville. And during that time, you actually gradually expanded your array of weapons to understand galaxies into radio interferometry, actually moved to larger distances by doing, I think, leading the Cosmos VLA survey for the Cosmos fields. And that accompanied you for many years thereafter, and you gradually moved down from the luminous objects to the less luminous objects, which were actually tracing the star formation. And it's noticeable reading through your career that you've always tried to do that, which I think is really nice. I mean, you try to also look at the free continuum as a way of doing this too. So this is all part of the same trend. And then following a Jansky postdoctoral fellowship at the National Radio Astronomy Observatory, where I think you were working with the radio continuum, you actually moved to Heidelberg to a permanent position as a staff member in the Max Planck Institute for Astronomy, where you are to this day. And it was then that you again expanded out into high-resolution optical spectroscopy, looking at galaxies. Again, you kept your interest on the AGN side of things, but you still were gradually getting into the high-resolution imaging of star-forming galaxies, and that culminated actually with this amazing picture of M51, which was the first real sharp look at the gas in its relation to star formation in a galaxy of any kind, except for the Milky Way. Of course, in the Milky Way you can't see it anyways, but and actually that was at that point she was already doing her second Heidelberg Astronomical Colloquium, and it's extremely rare that we ever have somebody giving a third, but in Eva's case it's completely unavoidable because of the huge work that you've done moving the field on. In particular, since that 2016 colloquium, you have introduced the FANG survey, which actually combined everything together, including spaceborne optical imaging, to get a complete overview and detailed panchromatic view at high linear resolution of all the nearby spiral galaxies and star-forming galaxies. Along the way, you had various awards. I just mentioned one, which is the ERC Advanced Fellowship, which was 2016, I think. And anyway, enough of me. Let us sit back and enjoy this overview of what really goes on in galaxies from the person who knows it, perhaps best of all, Eva. Please go ahead.
So, thank you very much. So thank you very much for giving me the opportunity to present to you first the FANG survey that stands for Physics at High Angular Resolution in Nearby Galaxies. What you see here in the background are some of the galaxies I'll talk about. So the aim of this is today basically to understand what we have learned from a star formation process when we move to a scale of a cloud, so a giant molecular cloud or an H2 region, and what to understand. So to rephrase that question kind of differently is basically we want to understand which physical processes control the formation of stars. And in order, the standard processes that you hear from your colleagues like Ralph Klessen, who's very much into small scales, and our understanding star formation in our galaxies is, of course, you need self-gravity or gravity. There's turbulence. It's either injected on small scales by stellar winds, supernovae explosions, but you also can think about turbulence being injected by having spiral arms or bars that are driving the gas flow throughout the disk, also causing turbulence. And the last point I want to mention is radiation. I'll ignore happily cosmic rays or magnetic fields because they are observationally very hard to tackle. The other thing to think about how to understand what controls star formation is to ask which is the scale I'm basically studying it. And if you have been up to MPIA, you know that people have been very big in using galaxy cosmological surveys, look-back surveys, looking at how galaxy populations as such evolve over cosmic time. If you move to nearby galaxies or resolving galaxies, you can understand how much of the disks or the environments within a galaxy might be important to control the star formation process. You go down to individual star-forming regions, like a cluster formation that is optimally studied in the Milky Way, and then you end up with a star. So depending where you go is basically what insights you can gain on the star formation process. So to think about as a galaxy, you can think about a galaxy as kind of an ecosystem. You have gas that gets accreted from the intergalactic medium. It somehow ends up on the disk. Within the disk is a whole range of processes happening, star formation. You can study the stellar population, star formation history, getting an idea how this mass buildup happened in the galaxy, how the gas flows within the galaxy. You have metal enrichment happening through star formation. In the center, you have maybe a nuclear cluster, very likely if you look at massive galaxies, a supermassive black hole. Those might then drive an outflow by the AGN activity or the star formation, and that gas might be being pushed back to the halo or the intergalactic medium. And again, as I said, you can use galaxy populations, environments, or star clusters, and what they tell you is basically how global properties in galaxies affect the star formation process. With studying resolved galaxies, how local properties within the galaxy might have an impact, and then if you go down to star clusters, you really get down to the detailed physics. So for this talk, I will basically focus on the galactic environments and the local properties, and I will only focus on one of the processes that are happening in the galaxy ecosystem, and that is the star formation, or as you can also think about it as the baryonic life cycle. So the baryonic life cycle, if you see the galaxy here in the middle and you just take out a little parsec of a few hundred parsecs, you basically will find a whole range of ingredients there. And if you think about the life cycle process here is you start off with a diffuse cold atomic gas. At some point it becomes more dense, molecules can form. Those molecules, molecular structures can start to condense, start to collapse and form stars. During the process of the star formation, you have radiation or winds. They inject the gas over the surrounding birth cloud. You start to have H2 regions, supernovae go off, disperse the gas even more, and you have stellar ejecta. Then you have ionized gas. This ionized gas at some point can kind of cool again, and you have basically are back to the diffuse atomic gas where the cycle starts again. All the little symbols you see on the bottom, they basically represent telescopes across the electromagnetic range, and you see with the different components of this that you need to observe and combine them to basically obtain a full cycle of this, a full picture of this baryonic life cycle. So for the course of this talk, I will just focus on going from molecular gas down to basically the end products, the young stars. And questions I would like to address are basically where, when, and how do stars form? How efficient is star formation? Is it the same everywhere? how long does it take to form a star, or how long can star formation proceed in one part of a galaxy, and what shuts off star formation? And I will touch upon some of these aspects with the recent results. So before you kind of do that, the question is, where and how do we study the star formation on a cloud scale view? So we kind of know that the majority of stars form in main sequence star-forming galaxies, and I'll tell you why ALMA is such a great instrument. So, so the first thing is the ALMA revolution. So what you see here on the left-hand side is a single dish image of the central 9 kiloparsec of the nearby galaxy M51, or whirlpool. You see very nice structures. In the 2000s, a large number of surveys have started to study molecular gas in the nearby local galaxies 50 to 100, and they have helped better to understand what is driving star formation, namely molecular gas. On the right-hand side, you see the picture, the same picture now obtained with a plateau de Bury interferometer, and the difference between the two galaxies is just the change in resolution by about a factor of 100. This is the M51 picture that Richard alluded to. And so what you see is basically going from KPC resolution to cloud scale resolution, you obtain a much different view of the ISM. So the thing, what was great about Plateau de Bury, it allowed to do this, but this took about 200 hours of observing time, so clearly you can do it for one galaxy, particularly if it is partially bright. But ALMA now allows it to do it with 2 hours using its 12-meter array. So starting off with the first set of 12 galaxies, Jai's Sun looked at the distribution of the line width on the y-axis versus the stellar molecular gas surface density on the x-axis, and you see that basically the galaxies are spanning a wide range, but they do so in a kind of systematic manner. And if you look at along the diagonal, that is, you see that basically the ratio of kinematic to potential energy is roughly the same. Therefore, the gas seems to be in correct partition. Whereas if you look along the dotted lines, which is basically how you would quantify the turbulence, that there is a large range of internal pressure that the clouds experience. And this has been put forward, for example, by Annie Hughes, but also others, but found that the cloud internal turbulence, as measured here, compared to the external pressure that is basically set by a weight of the gas and the stellar disk, that they are roughly similar and that they are in balance. So taking a significantly larger set of our galaxies, Jai's Sun set out to test this. And what you see here is on the y-axis, the turbulence measured, the internal turbulence measured, turbulent pressure, measured at 120 parsec versus the external pressure as inferred using a measurement at about 1 kiloparsec. So you see that there's a very nice correlation. However, if you look in the bottom part, you see that basically compared to the red line, which is the one-to-one line, the clouds appear to be overpressured. And the nice thing that Jai did here, he basically also took, in addition, he took into account the intrinsic self-gravitating pressure, so the weight of the cloud itself, to understand how this contributes to the external pressure. And then you would see here is basically that the cloud internal pressure and the external pressure, taking into account the cloud's own self-gravity, moves things basically on a one-to-one line. So then the question is, do cloud properties or molecular gas properties change if you observe them in different types of galaxies? And what you see, yeah? Okay, so the question was basically, what is causing, causing the difference between the left hand and the right hand plot, and if it is indeed taking into account the self-gravity of molecular cloud, then helps to balance the internal pressure. I hope I rephrased that correctly.
And gravity is more important than the external pressure involved in these clouds together?
I think what you basically see is that there the self-gravity dominate is also, for these clouds, is all of these systems are sitting in the part where the cold ISM is dominated by its molecular gas mass. So any contribution from the atomic layer is very low. And you see also when you go to the lower part, ambient pressure dominates, is when the molecular structures are sitting in the atomic weight. So that it makes much more sense that this contributes much more. So it's basically also taking into account the phase transition that is happening in the cold ISM. Which brings me to this plot again. So global star formation rate versus global stellar mass. So basically the question is, so what you see in the color of the points is that the average surface, molecular surface density is increasing if you go to more massive systems, which basically tells you that the way the observations were set up, we are starting to probe more and more a molecular dominated phase, which is much more prominent in more massive galaxies. If you go above and below the dashed line, you don't see much of a color trend, which could have been expected, but it's not. So clearly there is some variation with the global galaxy properties. These galaxy-to-galaxy variations, you can also, this is a very interesting experiment because it took 10 galaxies and made the data exactly the same at 90 parsec resolution. It had the same spatial angular resolution as well as the same noise properties, so quite a bit of the good data sets were degraded. And what you see is the distribution of per galaxy in a colored line of different parameters that you can extract for the cloud properties, and you see that there is quite some variation even among these 10 galaxies. Another way to look into now breaking up galaxies in different environments. So here you're seeing the line width plotted again against the surface density, and you see that the gas that is sitting in galaxy disks, shown in blue, has one correlation. Whereas if you particularly look in the centers of barred galaxies, like our own Milky Way, you see that those exhibit both higher line widths as well as higher gas surface densities. And another nice result was in Dry's paper here, is that the molecular gas surface density, if you look at the same radius in the spiral arm versus the interarm, there seems also be a small but significant enhancement of the gas surface density. So all of this kind of points to the fact that there could be variations due to the global galaxy properties as well as to the galactic environment. And this paper by Jai-sun, which appeared a couple of weeks ago on AstroPH, looked into these properties at 150 parsec resolution. There are different like mass, radius, surface density, pressure, whatever. And the other metric there is looking into local environmental metrics like what is the radius, the average molecular gas surface density, stellar mass surface density, and so on, and also in global galaxy properties. And I don't want to go into details, but the thing that you see, the darker or brighter the colors are, the stronger is the correlation or anti-correlation. And what is becoming clear is basically that always the local environmental matrices have a much higher, stronger correlation. And so this kind of points to the fact that it's the local environment that is more important in setting the properties of a molecular gas at 150 parsecs rather than the global properties. And you could kind of come up with a speculation, I call it, that the galaxy-to-galaxy scatter that we are seeing is basically driven by a variation in local environments, that certain types of galaxies have just a certain subset of environments that are better for setting certain conditions in the galaxies. And so this basically leaves me that the structure is set by a balance of internal and external pressure, and that it's the local properties within galaxies that matter, rather than just using the global properties. Moving on to the star formation, so basically turning gas into stars. There is a very simple test one can do. You basically ask, I take my distribution of molecular gas, but you see on the left-hand side, and compare it to my distribution of a star formation rate tracer here, H alpha emission, and I'm just asking how many sidelines or pixels I do find both tracers, and where that you see here in pink, and I would call that star-forming gas, and how much sightlines where I see only the gas, or CO, and where I only see VH alpha. And by doing that, I can ask, so do I see a variation of this star-forming gas with stellar mass? So what you see here is the typical fraction in galaxies broken up in 3 mass bins, and it's basically more or less constant. However, if you look at the CO-only fraction, it's much higher in more massive galaxies, which kind of makes sense because there the gas surface brightness or density is much higher, and the same then is the opposite trend in the star formation tracer. We also were wondering if this fraction of star-forming gas showed any trend if a galaxy is sitting below the main sequence or above, which is basically what you see in the x-axis here. And you see that the overlap fraction is more or less constant, scattering around 30%. And also the color, you don't see a real trend, except that more early type galaxies tend to sit below the main sequence. Its picture changes if you go to look at the CO-only sightlines. There again is no trend across the main sequence. However, in the color coding, you see that in early type galaxies that contain molecular gas, you have a very high fraction of CO-only sightlines, whereas in the more late type galaxies, which also tend to be more low mass, it is much lower. So, but clearly there are some trends again. Now you can basically take the fraction, how long do I see molecular gas? Do I see it being star forming, and see my star formation rate tracer? You can come up with and use that as a fractional scale, and combine that with a time scale, like for how long you can see H alpha, and then you get kind of a cycling time, how long your molecular clouds or your molecular gas is visible. And Xianpan did that, basically looking how this scaling factor is changing as a function of resolution. So the dark points in 1.5 kiloparsec, whereas the magenta point is 150 megaparsec, and this is in the set of our low mass end of the sample. And you see that basically the more you increase the resolution going from dark gray to magenta, that this fraction, this scaling factor is dropping. And the interesting thing is, if you do that, look now at the other 2 mass spins, you see that the life cycle of the clouds appear to be becoming much longer if you go to the centers of very massive galaxies. So overall, they appear to be short in low mass galaxies and longer in high mass galaxies. There is the caveat that also the tracer has some dependence, how well you can trace molecular gas. And what you see here is the cloud lifetimes you would infer. So basically this is 1. If you assume H alpha is visible for 10 mega years, you come up with 10 mega years, 10 to 20 mega years, and this is very similar to other measurements, for example, by Melanie Chavance. The thing to take away is also that you need to basically resolve the individual constituents. Another way to understand how much star formation might vary across a galaxy is to look at a galaxy and break it up by its environment. So going from the center in red to a stellar bar in green, spiral arms in blue, and then disk in gray. And that is work done by Miguel Carreta. And what you see here is that molecular gas surface density, shown on the left, is high in the center, and it's accompanied by a very high star formation rate surface density in the center. And then in the other environments that are in the disk part, there are slight but still distinctive differences between the different environments. The one thing that is interesting out of that study is, here's looking in the right-hand image at the ratio of the depletion times in the center relative to the disk. And the barred galaxies show a much larger diversity compared to the unbarred galaxies. So clearly something is happening with gas inflow or consumption in barred galaxies like our own Milky Way. Moving on to the star formation scaling relations. So typically, particularly if you work more in with cosmological surveys, there are three observables are used to describe the star formation process in galaxies. It's stellar mass, star formation rate, and molecular gas mass. The star formation rate versus stellar mass is the star forming rate sequence I already introduced in the beginning. The other one is star formation rate versus molecular gas mass, also known as the Kenniker-Schmidt relation, and I'm sure many of you have heard it in different contexts. The third incarnation or permutation would be molecular gas mass versus stellar mass, and this had very recently been called molecular gas main sequence, though it has been studied as a set of parameters already for many decades. So these three parameters can either be studied using the masses or the surface densities, and those are basically the scaling relations. In the bottom, you probably can't see. This is a compilation of observations that have been done at kiloparsec to sub-kiloparsec measurements of these relations, and the values are here. So the question was, do we still see these relations emerge if we look at data at 100 parsec resolution? And using 18 galaxies from thanks, Ismail Peza has basically demonstrated the scaling relations exist, albeit with significantly higher scatter. And it was not necessarily clear that indeed we would be able to recover them. In order to do it correctly, you have to be careful how you account for your non-detections. So the first thing we thought to look at was how the galaxy-to-galaxy scatter is changing. And so you here the three panels show the three different relations. The dark arrows, the black arrows point to the global slope you saw on the slide before, whereas the dashed lines give you the median of the individual slopes. So you see that they are not necessarily all the same. The galaxies are basically sorted every time by NGC number, and if there would have been any trend with color sorting, that would tell you that there is some relation with stellar mass, or with the size of a symbol, that would tell you that there's some variation scaling with the global star formation rate. So there are no global trends with star formation rate stellar mass. The one thing that comes see is basically there's the smallest scatter between galaxy to galaxy if you look at the Kenniker-Schmidt relation, which is star formation rate versus molecular gas mass, which kind of points you to the fact that probably the star formation process throughout the galaxies is kind of more homogeneous. Another way to look at it is basically to break up the galaxies into environments, as I showed you before. So these, again, are the scaling relations with three. Now, basically per environment, so the dashed black line is the global, and then the colored lines show you the different environments. And if you focus on the light blue line, you see that this always tends to lie above the global relation. The disks normally define them. Bars in the light cyan color lie below, and the centers are more or less all over the place. But so by looking at these, it could still be that if you think that the star formation rate surface density is maybe driven by a combination of the stellar surface density as a proxy for the gravitational potential and the molecular gas, you could think about that there's a 2D plane in the 3D space set up by these parameters. And this is basically a way to describe it and has been proposed for observations at kiloparsec resolution. And Ismail basically looked if indeed he could find a solution for the different environments that all would end up in the same place. And it's clear there is these environments are not sitting on the same 2D plane, but at different corners in the 3D space. One quick point to make is about the star formation efficiency per freefall time. That is basically you take the freefall time of a cloud and combine that with the star formation rate that is happening in that cloud. And from theory, you basically expect that about 1% of the mass of a cloud is converted into stars. when you average across the population of clouds in disk. And this work by Diaz Otomo was the first attempt to quantify that using 12 galaxies. So in the bottom you see the star formation efficiency per freefall time. You see the distribution in color he gets from the different set of galaxies, cutting them with different resolutions. On the top in black are different measurements, mostly in the Milky Way. The gray vertical line is the theoretical value, and then on the right-hand side, you see basically what happens if we change number of the assumptions. So overall, the conversion of gas that is present in a galaxy molecular gas is fairly low. And that basically, just to summarize that quickly, is that the efficiency of clouds to form stars varies across galaxy disks, particularly between center and the disk environment, but also in the disk environment, and also that the star formation process proceeds fast. However, overall, it's more or less it's very inefficient. The last few minutes, I want to just make a few statements about stellar feedback. So if you think about this is the process of how a cloud evolves, basically from the cloud collapse, star formation, feedback, disruption of the cloud dispersal. There's molecular gas structure present up to a certain degree, and then the question is, what is the stellar feedback that is causing the disruption of the cloud? Is it pre-supernova feedback, so it's a feedback happening before 3-something million years, or is it indeed the supernovae that do most of the work? And in order to attack that, to understand this a bit, Ashley Barnes has taken the H2 regions in the Muse sample and basically looked into two extremes, trying to use also line diagnostics to infer the properties. So the problem is with H2 regions in Muse are mostly unresolved. So below here you see HST images, so you see shells, leaking systems, and so on. So he had to basically go back to the two scenarios in the top, where first he assumed that basically the pressure is coming mostly from a large diffuse area, or it's indeed the little compact parts in the inner part of an H2 region, the clumpy H2 region. And based on that, he can get an upper and a lower bound on the pressure that the H2 region might exert. So he was assessing basically the thermal gas pressure, the direct radiation pressure, and the wind ramp pressure. And if you plot basically the combination of these pressures, here he's only taking into account the thermal gas pressure and the radiation pressure as the radius that is measured or inferred for the H2 region. You see that the points he's getting in red are similar to what you have been measured, for example, in the Magellanic Clouds, and they fall roughly along the line that you know from measurements in the Milky Way. So the other point was to see how much of this H2 region internal pressure, how that relates to the external pressure, so dynamical equilibrium pressure. And you see basically if you assume that everything is very clumpy, most of the H2 regions are overpressurized, independent of the gas surface density, so they would basically disrupt molecular gas. If you think about everything is smooth, then you see basically if you go to the centers of galaxies where you have high molecular gas densities, that H2 regions might be no longer very efficient to breaking up the molecular gas completely. And the last point is work here by Liz Watkins and Catherine Crackle's group is about molecular gas superbubbles. So she looked through 70 plus galaxies in order to identify superbubbles that have a radii of about 150 parsecs or larger. Here I'm showing just a subset. She also looked for kinematic signatures that this indeed are superbubbles. Then she selected 31 that contain young stellar associations. So now you see the associations in blue, and H alpha in purple, and molecular gas CO is in brown to, or golden to yellow. The nice thing about that, she could infer the age of the bubbles by using the CO expansion velocity, as well as by fitting the age of the stellar clusters using the SED of these clusters. And so what you see here, surprisingly, if you compare the age of these HST clusters on the y-axis versus the age of the bubble using the CO, that they fit a very nice line. There's still, it's not one-to-one, which could be explained by some assumptions made about the expansion velocity. And the part that is very interesting is also that all the bubbles that are older contain kind of a supernova. So this kind of tells us that supernovae must help destruct the molecular gas. So here, basically, it's the pre-supernova processes are important, protonization, wind, and the role of the supernovae is not completely clear, because if pre-processing is important, then the question is, what exactly is the role that the supernovae are playing, and does it vary with the environment in the galaxies? So kind of what is next? I think there are two nice features. One is the role of the dense molecular gas phase, and the other one is the importance of the embedded phase of star formation. So the dense gas fraction, we know basically in the bottom it's the fraction of dense molecular gas to the bulk of molecular gas versus the star formation rate efficiency of a global molecular gas. And what you see is a trend, what you kind of expect. These are measurements from the Empire survey that was led by Frank Bigil and started while he was still here as a CLISO fellow. And you see basically the star formation efficiency goes up if the dense gas fraction goes up, and this is kind of what you expect. The interesting part comes if you're looking at the fraction of the star formation efficiency of the dense gas, and that kind of drops if you have higher dense gas, and which is a little bit unintuitive. The following explanation has been put forward. This is a cartoon done by Adam Leroy. So if you think about the dense gas distribution of a cloud that is sitting in the disk of a galaxy, you basically see the two red lines, which are basically marking our tracers, and a cloud in the disk. You basically, with a dense gas tracer, we're perfectly tracing the part that is good as forming stars. Whereas if you move the cloud into more into the center of a galaxy, you have higher surface density, higher line width, and that basically it's the higher turbulence in the cloud that stretches the density distribution, and a larger part of the cloud becomes now observable at the dense gas tracer, and not only the star forming part. So in order to test that, they are starting the survey with a plateau de Beer interferometer to obtain cloud scale tracers of various dense gas tracers. And so this is hopefully one of the next signature images coming out of NOEMA. And the other one is JWST. I assume most of you are aware, next Tuesday is the release of the first pictures. So we are very excited about tomorrow, about an hour from now. They will observe this galaxy, and the hope is basically to understand if there are the embedded star formation regions in here. Quick advertise again, all the data I've showed, most of the data I showed in this presentation is public. You can get it from our website or from the observatory's archives, which just means you have access to about 100,000 giant molecular clouds, 20,000 H2 regions, fully characterized. Catalog is in the making, and also information for the stellar clusters to be released at the IAU in about a month. And also JWST is observing. The program that we have is a treasury program. That means all the data will become public immediately. There's way more results than I was able to talk about on feedback, H2 regions, gas flows, structures, stellar clusters, dense gas, line diagnostics, molecular cloud properties. I showed you there are many of us in Heidelberg, so please check and talk to them. And that basically brings me to my conclusions about the star formation process and cloud scales. I think we gained a lot of insights thanks to the statistics of thanks ALMA. I hope to convince you that indeed you need to reach the scales of star-forming units to get a better understanding of the timing of the cloud evolution, that molecular gas at those scales is close to energy equipartition, that the local properties in the galaxy matter, how the gas properties are formed, that star formation is clumpy, inefficient, but once it starts, it proceeds fast, and both pre-supernova feedback and supernova feedback are important. I think the relative roles are still unclear. And finally, I also would thank to all the observatories and their staff that helped us to put this great data set together. Thank you.
Thank you so much, Eva, and to all your collaborators too. It looks like it's quite well coordinated, and I think that's something we're all very grateful for, because this is going to be a treasury for many years to come. Now, I would like to first of all open the floor here for questions. If the Zoom audience could indicate by raising their hand or by typing in that they would like to pose a question, then we'll come to you shortly. So, any questions in the hall? We already had Hans Walter. Let me ask a question about the scaling relations. Actually, I genuinely don't know what's going on with the scaling relations, because you showed, for example, there were different scaling relations sort of running parallel to each other. And is this something which is just separate scaling relations, or is it sort of a temporal variation going up and down, oscillating above some central plane? Is there any data information, since you do have some time resolution information, that you could bring to bear on that?
Okay, so the scaling relations are, I think, what they are telling us, at least from our high resolution data, I think is that indeed it's the amount of molecular gas that determines the star formation rate you see, that there have been discussions in the literature, and particularly if the resolution is a few hundred parsecs or more, that people were arguing that is indeed the underlying potential. So the star formation, the stellar mass surface density that is controlling the amount of molecular gas, which is controlling the amount of star formation rate you see. And I think there's something in addition to the stellar surface density, which is not the complete proxy of the stellar potential, that is helping to determine the final star formation rate. So the connection between the molecular gas surface density and the star formation rate surface density is closer at our resolutions. And also the variation between the environments. This has the smallest scatter, they chose that. So that, yes. So I leave it there. I think there are other parameters that help control how much of parcel of molecular gas forms and then forms stars. That is not captured by the stellar mass surface density.
Okay, that's interesting. Well, I mean, would it be interesting to get the neutral gas into this picture?
Yes, it would. It would be very much, particularly, I mean, we are currently focusing on galaxies that are similar to the Milky Way. We are focusing on the part where are dominated by the star formation rates. So we are in the part mostly there the cold gas is in molecular dominated. We are not in the atomic phase, dominated phase. So if you were to move to dwarf galaxies, a lot what I've said will become more different or look differently, and getting H1 observations similar to that resolution would be awesome. We are trying to get some more at lower resolution, so I think most of the thanks galaxies have H1 observations at a few hundred, half a kiloparsec, up to kiloparsec resolution, so that is started to be folding in.
It's amazing that radio astronomy in the 50s is now inverted, that the H1 is trailing. Okay, I think there was another question from the floor. Ralph Klessen. Yep, I'll just come to you with the microphone.
So this is super cool and very exciting and will keep us busy and the team busy for, I think, many years to come. But the question remains, what's next? I mean, can this be extended to much larger volume, possibly to the high redshift universe, or will this be for the next, I don't know, 10, 20, 30 years the legacy survey or database for these type of studies? How can this be extended to, let's say, more extreme environments, different metallicities, higher redshifts?
I'm just looking at Oleg, who's sitting there, who's very interested in looking into dwarf galaxies, pushing the ionized gas properties there. So I think on the optical IFU side, I think pushing to more low mass galaxies will be easy and possible, easy to do. Increasing the coverage of a current sample is something we hope to do. You know that well. ALMA, pushing ALMA to low metallicities is almost impossible because the CO is not a very good tracer in the low metallicity environment. So we would need there a better tracer of the cold molecular gas. And I think there's a big debate. It's unclear. Potentially, you would need to have a space mission that would allow you to observe the C+ line, so where you can trace basically the envelopes of the molecular gas and get a much better handle on the distribution. Pushing to higher, that was molecular gas, yes. I think doing a larger sample in the CO will be hard with the current ALMA array. You'll need more. I think at high redshift, people are starting to obtain observations of 100 parsec of nearby, of redshift 1, 2 galaxies by looking at lenses. So I think that is possible. Again, I think if you want to do large samples, probably you need to increase ALMA. At NREO, they are thinking about something like 10 times ALMA. That is, I think, something for 2030s and longer. Pushing JWST will give us a very new insight, and I think if it's around for 20 years, I think adding the dust phase, embedded star formation will be a lot that can be done there. Yes, and I think SKA H1, I think the Meerkat data is very impressive that can be done. If they have longer baselines, there'll be a lot that can be done on the H1. But I also think, yes, hopefully, I hope, fingers crossed, radio continuum will become more exciting.
Yes.
I think I fully ignored magnetic fields. I think one reason is they are hard to observe even in external galaxies. Sophia had done a number of observations, but it's now in its last leg. So I think in the radio, probably people can do something more. So I think there's always more opportunities. And I'm also hoping that the theorists and the simulators are catching up and helping us interpreting all the data.
Yeah, we better get going. No, I mean, the radio would be really, I guess you get some radio from Meerkat.
Yes.
I mean, continuum.
We have radio continuum from Meerkat for a small subset of galaxies. We are looking at the 10 centimeter radio continuum. The data just came in, so we haven't completely digested it. Basically, as a first start, I think NGVLA, if it lives up to its promises, it will be awesome to get at the dense gas phase. But even for ALMA will be hard.
Yeah, I mean, with that multi-wavelength data set, you'll be able to really see the pure synchrotron as well, which would be, I mean, for all the cosmic rays enthusiasts, would be also really exciting, you know.
Yeah. So the hope is this is basically a starting base, and people can add.
All right. I'm told that there are no questions from Zoom. Before we go and drink our cool beers, I mean, is there a chance, any more official questions? I'm sure that you'll have a lot of further chat in 5 minutes. I don't see anything. Then, as it's just 2 minutes past 5, I'll just then end with my formal announcements. Matteo Cantiello will be coming and telling us all about high-resolution simulations of stars and in 3D. which is now an exciting new branch, not only of astrophysics, but there it is, well done, but also physics. You can just see in one of his, so we're going into even much smaller scales, which is sort of another very interesting part of astrophysics these days. So, as I mentioned, now I've got some cool drinks. I hope they're still cool, just outside. So please come and help yourself, and take the opportunity maybe to chat further to Eva and maybe amongst ourselves. So, thank you very much, Eva. We wish you all the best for this continuing odyssey. We'll keep our eyes open and certain that many of us will get actively involved as well. Thank you very much.